In this lecture, we will see a very useful principle from combinatorics known as pigeonhole principle. The principle is extremely simple, so simple that it is difficult to imagine that this can be of use. Okay. The principle is very simple to state. Suppose you have n objects, say n balls, and they are distributed into k bins. If n is greater than k, then there will exist a bin with more than one ball. So, that is the principle. So, if you have n balls and they are distributed into k bins where n is greater than k, then there will be a bin, at least one bin, which has more than one ball. Okay. It is almost self evident. If the number of bins is small and if all of them had less than or equal to one ball, then the total number of balls is going to be only, it is going to be less than or equal to k, but the number of balls is greater than k, and therefore, the statement must be true. So, let us see some applications of this. So, pigeonhole principle, of course, it is very simple to state. The power of this principle comes from the wide variety of ways in which you can set up balls and bins. So, let us look at a problem which can be solved using pigeonhole principle. So, let us look at this sequence. So, consider this following sequence consisting of numbers 7, 77, 777 and so on. Okay. So, the ith element of this sequence would be 7, 7, 7 so on I times. Okay. Now, let us look at, so the theorem or the result states that there will surely be an element in this sequence which is divisible by, let us say, 1903. Okay. So, one element of this, there will be an element in the sequence which is divisible by 1903. Now, how do we prove this? What is the method? Is this, I mean, first of all, is this statement even true? Why should there be an element in this sequence consisting of 7s, the ith element being 7 repeated I times. So, one of these is going to be divisible by the number 1903. There is nothing sacrosanct about 1903. There is a wide, I mean, you can substitute it with a lot of other numbers. The few numbers that you can't, you can look at the proof carefully to figure out what all numbers can come in place of 1903. Okay. So, let us try and work out a proof for this. So, we will set up the balls and bins in a certain way such that we can argue that there will be a bin which contains more than one ball, and that is going to be used to construct the proof of divisibility. Okay. So, here one of these numbers to be divisible by 1903. So, what we can do is try and divide these numbers by 1903. You will get infinitely many numbers. So, let us just take, let us say, 1903 elements of the sequence. Okay. So, 7, 77 and so on. We will look at the first 1903 elements of this sequence and divide each one of them by 1903. You will get some remainder. Okay. If any of them is 0, then we know that we have some number in the sequence which is divisible by 3. What if none of them is 0? Okay. So, that is the case that we are interested. So, let us write down the steps. Consider the first 1903 elements of this sequence. So, divide the elements by 1903 and note the remainder. Okay. If any of the remainders were 0, then we are done. We have a proof that look, we have an element which is divisible by 0. So, we may assume that all the remainders that we get are numbers between 1 and 1902. So, remainders are between 1, both numbers inclusive, 1902. Okay. So, these are 1902 numbers, the remainders, and we have 1903 numbers in total. Okay. So, if you denote the remainder by R1, R 1903, so on, these are 1903 remainders, and each of them is one of these numbers between 1 and 1902. So, one of these remainders must repeat. So, let us say AI leaves remainder Ri, and Aj, where j is greater than I, leaves remainder Rj. So, we have this case that Ri is equal to Rj. Okay. So, what we have is Ai is equal to some number k1 into 1903 plus Ri, and Aj also has a similar equation. This is equal to k2 into 1903 plus Rj. We have Ri and Rj as the same, and therefore, if we do Aj minus Ai, what we will get is k1 minus k2 into 1903. Okay. Now, this 1903 therefore must divide Ai minus Aj. Okay. We are almost done. What we wanted to show is there is an element in this sequence which is divisible by 1903 and not the difference of two elements. Okay. But this is good enough for us, because what is Ai minus Aj? So, if you look at Aj, Aj is equal to 777 j times, and Ai is equal to 777 I times. If you subtract them, what you get is Aj minus Ai, that is going to be 777, and the last I terms are going to be 0, 0, 0, 0, 0. Okay. So, this is equal to Aj minus I, which will consist of j minus I sevens into 10 to the power I, because there are I zeros, this equation is true. So, we can write k1 minus k2 into 1903 is equal to Aj minus I into 10 power I. Okay. So, now if you look at 1903, 1903 does not have any common factor with 10 power I, because the only factors of 10 power I are 2, and the only prime factors of 10 power I are going to be 2 and 5, and they do not appear in 1903. So, 1903 must divide Aj minus I, and Aj minus Y is one of the elements in the sequence. Okay. So, we can say therefore, Aj minus I is the required element. Okay. So, that was one application of pigeonhole principle. So, the balls are the pigeons where the remainder that is left by each element of the sequence when divided by 1903, and the pigeonholes or the bins were numbers from 1 to 1902. We took 1903 remainders to fit in 1902 bins. So, now let us see another application of pigeonhole principle. So, a little more involved application. So, here we start with an irrational number. So, let us say E you can replace it with any other irrational number and we consider its multiples, okay, so 2e, 3e, 4e and so on. So, this is the sequence that we are considering. Instead of the rational number, if we had started off with a rational number, then we know that at some point of time we will get an integer. Okay. When we start with an irrational number and if you consider this sequence e, 2e, 3e and so on, the multiples of e, so we know that none of these elements in the sequence is going to be equal to an integer. But what we will show is one of these elements is going to be arbitrarily close to an integer. There will be some element which is, you give a measure of closeness, one of those elements is going to be arbitrarily close to some integer. Okay. So, we will make the, we will make the statement a little more concrete. So, let us say our degree of closeness we will call it as 10 to the power minus 100. Okay. So, we will what we want to, so this is what is delta, we will claim the following: for some n times e is delta close to an integer. So, delta close means so if I write the square bracket alpha, this will denote the nearest integer to alpha, okay. And if it is exactly midway, then we will choose either one of them. In that case, let us say we will choose the larger one, okay. So, this is the definition of the nearest integer. So, what we want to say is NE, so NE minus NE, okay, the number minus its nearest integer, its absolute value is going to be less than or equal to delta. This is the claim. So this is the definition of delta close, and what we are claiming is for some n, NE is delta close to an integer. Okay. So, how do we prove this? What should be the balls and what should be the bins? Okay. So, let us look at each of these elements E, 2E, 3E and so on. Here we have delta is equal to 10 raised to minus 100. Okay. So, 1 by delta is what we will choose as the number of bins. So, we haven't yet told what is the bin, but the number of bins will be, we are going to set up a balls and bins analogy, wherein the number of bins will be 1 by delta or 10 raised to 100. Okay. And we are going to look at 10 raised to 100 plus 1 numbers of this sequence, okay. And each of those numbers is going to be put in one of the bins, and since there are 10 raised to 100 bins, one bin is going to be containing 2 numbers, okay. Now, let us decide how we are going to put these numbers in the bins, okay. So, look at any number, if you consider let us say m times e, and if you look at the floor of that, this is going to be an integer, and me minus floor of me is a number which belongs to 0 comma 1. It cannot be 0 or 1. So, we could have said the open interval 0 1, okay. But this is me minus floor m times e is going to be some number between 0 and 1. Now, let us just look at this interval 0 to 1 and split it into 10 raised to 100 equal parts. Okay. So, let us call this as f of m. Okay. So, for the mth element, f of m denotes the amount by which me exceeds the integer part of the number. Okay. So, fm, if it, so now we have split this into 10 raised to 100 parts, equal parts. So, each part is going to be of size 10 raised to minus 100. Okay. So, these parts are going to be our bins. Okay. And if fm falls in one of these part, then we will say that the number falls in that particular bin. Okay. So, if you had, let us say, 2.78, E is approximately 2.78. So, look at the, there is some bin which contains 0.78, and that will be where the first element will be there. Now, if you take 2E, that is going to be something like 5.5 something or 5.6 something. So, that is going to fall in a different bin and so on. Okay. So, each element we are going to put in one of these bins. Clearly, since we took 10 raised to 100 plus 1 numbers, sum 2 bin is going to contain the same, sum 2 bin is going to contain 2 numbers. Okay. So, let us say n1e and n2e fall in the same bin. Therefore, n1e is equal to some integer plus, let us say, delta 1, and n2e is equal to k2 plus delta 2. Okay. And delta 1 and delta 2 are numbers which fall in the same bin. So, if you look at n1 minus, so let us say n1 is greater than n2. So, n1 minus n2e is going to be k1 minus k2, that is going to be an integer, let us say k plus delta 1 minus delta 2. Okay. Now, delta 1 minus delta 2, both these numbers, by virtue of being in the same bin of size at most 10 to the power minus 100, their difference can be at most 10 to the power minus 100. So, that means n1 minus n2 times e, if we call this as, let us say, re, where r is some integer, re is going to be k plus, this could be negative as well. So, it is plus or minus some number epsilon, where epsilon is guaranteed to be less than 10 to the power minus 100. Okay. So, plus or minus is the, so epsilon if you assume as positive, and if delta 1 is greater than delta 2, then we can say it is k plus, in the other case we will say it is k minus epsilon. Okay. But whatever is the case, re is another element of the sequence, and re is going to be some integer plus a very small number, and by very small here we mean that it is going to be less than 10 to the minus 100. Okay. So, we have seen two cases of pigeonhole principle. We will look at a little more, slightly more general version of pigeonhole principle. Okay. So, here we will say that so this is the generalized pigeonhole principle. So, if you have let us say n balls and k bins, then one bin will have, at least one bin will have greater than or equal to n by k balls. Okay. The same reasoning as to why pigeonhole principle is true will be the reason why the generalized pigeonhole principle is true. If you have distributed n balls into k bins, then there surely should be a bin which has at least n by k balls. because if all bins contain less than n by k balls, then the maximum is going to be less than n by k into k, which is less than n. Okay. So, now let us see another example involving the generalized pigeonhole principle. So, here we will look at an example from geometry. A one sided, we have a square whose sides are 1 centimeter long. Okay. And we are putting, let us say 10 points, place 10 points inside S. So, let us call this as a square S, and we are placing 10 points inside the square. Okay. If you have large number of points, then there will be 2 points which are close to each other. Okay. That is the general statement. Here we want to say that when we have 10 points inside S, there will be 2 points. So, claim no matter how you place the points, there will exist which are, there will be 2 points which are within 0.5 cm of each other. Okay. Now, how do we prove such a statement? Okay. There will surely be 2 points which are within 5 centimeters of each other. Now, how do we try to see this as the generalized pigeonhole principle? One way to think about it would be to take, let us say, circles. So, consider circles of diameter 0.5 okay, and if you can somehow cover the entire sphere using 9 circles whose diameter is less than 5, then we know that there will be 2 points in the same circle. Okay. So, what we want to try and do is, we want to somehow place 10 circles or 9 circles okay, so that they cover the entire region. Now, here if you want a circle, maybe that is a little tricky, and there is going to be a lot of overlap. So, it is not very straightforward to see how this can be done, but there is a simpler way wherein you can split it into 9 parts. Okay. So, you can look at this particular square, and let us say we split it into 9 parts, natural split. Okay. So, it is split into 9 squares. Okay. Now, if you look at these 9 squares, and no matter how you place 10 points, there is going to be one particular square which contains 2 points. Okay. And the maximum distance between any 2 points in the smaller square is going to be, so smaller square is of side 1/3. So, this into root 2 will be the maximum distance, okay, and that is 1.414 something divided by 3, that is going to be less than, this is surely less than 0.5. Okay. So, if you have split this in this particular manner, so you can get 2 points which are within 0.5 centimeters of each other. We will end our discussion on pigeonhole principle by looking at one more example. So, here we are looking at a combinatorial problem where we have, let us say, 100 boxes and we have 200 balls, or 100 bins and 200 balls, and we are distributing these balls into these boxes following 2 rules. The first rule no box, no bin is empty. The second rule, no bin contains more than, let us say, 100 balls. Okay. Now, when you distribute it in this way, there are many ways of distributing it in this way. When you distribute, all of those distributions would have the property that there will be a set of bins containing. So, when I say a set of bin containing, you take all the balls in those bins together, whatever they contain. So, the set of bins containing 100 balls, exactly 100 balls. Okay. So, no matter how you distribute the balls into bins, there will be a subset of bins such that together they will account for exactly 100 balls. Okay. Now, suppose you had, let us say, 700 balls and we have done this. Okay, we could, let us say, give 7 balls in each bin, and that is never going to, if you distribute in that particular fashion, there is no way that you can get 100 by combining few bins. Okay. So, natural question would be to wonder why such a claim is true when you have 200 balls and 100 boxes. Okay. So, we will give a proof of this via pigeonhole principle. Okay. Again, the techniques are very similar to the techniques that we had seen. We are going to, when we want to say that some bin contains 100 balls, okay, even if we can say that some bins together contains a multiple of 100 balls, okay, the only allowable multiples under these conditions are 100 and 200, but if we skip some boxes, then you are going to get something less than 200. Okay. So, if you just say that there is a collection of bins which, there is a subset, strict subset which contains a multiple of 100 balls in them, then that would mean that it is exactly 100. Okay. And when we want to look at that multiple of 100, we could try and look at the remainders. Okay. Remainder of what? This is where the cleverness comes in. So, the proof. So, let us look at these boxes. They will contain some number, let us say A1, A2, A100. So, AI denotes the number of balls in bin I, okay, or we have just arranged it in some particular way. Okay. Now, we will insist one thing on this arrangement. We will insist that A1 is not equal to A2. Okay. Can this always be done? If there are 2 bins which contain different number of balls in them, we could of course get those 2 bins and do this entire thing. So, the only case where we cannot get such an arrangement is when every bin contains exactly the same number of balls, but that would be the case when every bin contains exactly 2 balls. But in that case our claim is trivially true, because we can just take any 50 bins and together they are going to contain 100. Okay. So, we will assume that that is not the case, and therefore, we have 2 bins A1 and A2 which has a distinct number of balls in bin 1 is going to be different from the number of balls in bin 2. Okay. And those numbers we will call as A1 and A2. Now, let us consider this sequence. Of 100 numbers. So, the first is A1, the next is A1 plus A2, the next is A1 plus A2 plus A3, and last is A1 plus up to A100, and this is going to be surely 200. Okay. So, let us look at these numbers and ask, sorry, this. So, this is going to, the last sum is going to be 200, the total number of numbers that are there in the sequence is 100. So, this is a sequence of 100 numbers, okay, numbers varying from, let us say, A1 to 200. Now, let us divide, so let us call these numbers as, let us say, B1, B2, B100. Okay. Let me consider the remainders R1, R2, R100. So, this is Bi mod 100. Okay. There are 100 remainders. If any of these were 0, then we are done. So, except R100, the last one of course is going to be divisible by 100. Of the other, so let us skip the 100th element, we will just look at the 99 elements. Let us say R99. Okay. So, these are 99 elements. If any one of them gives a 0, then we have a set of bins which contain 100 balls. So, we can assume that none of them is 0, and therefore, they are numbers between 1 to 99. If none of them is 0, then they have to be 1 to 99. Now, let us ask this question, is there any repetitions in them? Okay. There could be repetitions, but that would be the good case for us. So, if Ri equals Rj, that means the Bi's are increasing in order. Okay. So, if Ri equals Rj, then Bi plus 100 is equal to Bj. Okay. Therefore, if you look at the numbers or look at the bins numbered, let us say I plus 1 to j, they are going to be of some 100. Okay. So, now that would validate our claim. So, we may assume that that is also not the case. That means all these numbers are distinct, and therefore, they are numbers from 1 to 99. Okay. Now, what do we do? Okay. Here is where the assumption that A1 is not equal to A2 comes handy. Okay. So, let us look at these numbers and we will add A2 into the mix. And if you look at A2 mod 100, that should be, now you have 100 elements. Okay. A2 is itself not 100, because we said that no bin contains, say, greater than or equal to more than 100 balls. If A2 was exactly 100, we have one bin with exactly 100. Okay. There should be some sum here which is exactly equal to A2. Okay. So, if A2 is added, there will be a repetition. Okay. And that repetition, without A2 there was no repetition. So, that sum is going to be, so that remainder is going to be A2. Okay. And by virtue of A1 not equal to A2, so this is not equal to B1, it is going to be some Bj. Therefore, Bj is going to be equal to 100 plus A2. Since Bj is equal to 100 plus A2, if you look at the set consisting of all elements from 1 to j and remove the second element, we will get a set which contains exactly 100 balls. Okay. So, that concludes the proof, and we will stop here.